to delete them again because I think I have to reboot the computer after class, after the previous class or something. Yeah, I don't know. Okay, so 1 minus 1 minus 0, 1. 0 squared, 0. So L'Hopital's rule, limit, x approaches 0, e to the x minus 1 over 2x. Again, 0 over 0. Limit, x approaches 0, e to the x over 2. So this is 1/2. It's like a new function that works with L'Hopital's rule. Yes. So once I differentiate and I get this, I plug in again, and I realize it's 0 over 0. So it's like I start from scratch with a new function. I can apply L'Hopital's rule as many times as I need, as long as the conditions are fulfilled. Fraction and 0 over 0 or infinity over infinity. Yes?
This one's differentiate. Is that right? For the, I guess it was on test 2.
Yeah, do you want me to do 61 first, or?
Oh, yeah.
So 61. Limit, x approaches infinity from x raised to 1 over x. And this is infinity raised to 0, which is one of the 7 indeterminate cases. So then I will denote by y. It's a function raised to a function. That's my only escape. Very good. Natural log y equals 1 over x, natural log x. Is this okay so far?
Yeah.
Okay. So now what do I have to do? I have to apply the limit now. I applied the log to y, and now I have to apply the limit. So the limit from... I apply the limit on the left first. So limit as x approaches infinity from natural log y equals limit as x approaches infinity from 1 or natural log x over x. And now this is infinity over infinity.
Right.
So that I have limit as x approaches infinity 1 over x over 1. And obviously this will be limit of 1 over x. So the answer is
0.
Now I take the beginning and the end and put them together. So I write limit as x approaches infinity from natural log y is 0. What do I do next? Yes, I swap the operators because the conditions are fulfilled. The continuity conditions are fulfilled. Natural log of limit as x approaches infinity of y is 0. And now I'm asking myself, what could this be? Yes?
How does it become 0?
So this must be 1 indeed, because only natural log 1 is 0. So then limit from x raised to 1 over x as x approaches infinity is 1.
Will we have to rewrite it again like that, or what if we just ended at 1?
I did write it again.
Well, no, I mean, On the test, are we gonna have to, or can we just leave?
Yes, you have to write the answer. The answer is limit as x approaches infinity from x raised to 1 over x is 1. Yeah. Good. Yes, you had a question
Oh,
from
no,
a previous test.
This is basically it.
Very good. So let's look at something else. Do we want to review how to graph a function using derivatives? Do we want to look at related rates? Optimization.
Yeah, let's do that.
Related rates.
Optimization, for sure.
Okay, related rates and optimization. I got 2 requests. Related rates. They are in chapter 3. Okay, page 249. I don't even know what else to. Bless you. We looked at the cars. We looked at the spotlight. We looked at a walking person.
How many questions we talking like final?
Well, you have it will be divided about 25% from each. 25% for test 1, 25% from test 2.
16 to 20?
Something like that.
We have 4 hours.
You can start at 2 o'clock if you want.
At when?
You can start at 2 o'clock if you want.
Okay, I go till 1. Yeah, I know.
What time's the final actually start?
I have no idea. I have to look it up. It's on the syllabus. I can look it up right now. It's at the end of the syllabus. Okay, right now. No, don't bring dinner, please. And you cannot take a break of half an hour. 7:45, 9:45. But since there is no other class but I'm here, so it doesn't matter when you
So
start.
if we come at 2, do we have till 9:45?
If you need to.
Yes, 7:45 p.m.
PM.
I mean,
That's fine.
Okay, 31. I don't know if we did this one. You let me know.
What page?
249. 31 on page 249. The top of a ladder slides down a vertical wall at a rate of 0.15 meters per second. So I'm going to write 0.15 meters per second. We'll see what that means in a minute. At the moment when the bottom of the ladder is 3 meters from the wall, so that's the first scenario. At the moment when the bottom of the ladder is 3 meters from the wall, it slides away from the wall at a rate of 0.2 meters per second. How long is the ladder? Maybe I shouldn't denote it by X, maybe we should denote it by H.
Are these the same?
The difference is shown that the top's still moving down at 0.15.
Yes.
Yeah, one's at 1.4.
I'm very confused right now. What's this?
Okay, so we have a ladder that is leaning onto a wall. And for some reason, it's sliding away from the wall. Okay. So the top of the ladder slides down at a vertical wall at a rate of 0.15 meters per second. You already identified it. I was just going to ask. So this point slides down at 0.15 meters per second. At the instant in which the ladder is, the bottom of the ladder is 3 meters away from the wall, at the moment when the bottom of the ladder is 3 meters from the wall, it slides away from the wall at a rate of 0.2 meters per second.
So what's the 0.15 meters per second?
It slides down the vertical wall. And this one is
Sliding now.
sliding away from the wall at a rate of 0.2 meters per second. How long is the ladder? So obviously, I'm going to denote this by X, and I'm going to denote this by Y. So for now, I do know that H squared equals X squared plus Y squared by the Pythagorean theorem. Okay, so now we know that Y changes with time. So Y is a function of time. We know X is a function of time, but we definitely know that H is a constant. No question about that. Okay, good. So then, what do we need to determine, basically? Yeah, if I determine X and Y, then I will be able to find H, correct? Okay, say it again. Yes, but we have to determine something else before we plug in that, right? So when it slides, when it is 3 meters away from, when the bottom is 3 meters away, then it slides away from the wall at 0.2 meters per second. So dx over dt equals 0.2 meters per second, but when x is 3 meters.
And then dy over dt is 0.15 and we don't know why.
dy over dt equals 0.15 meters per second. But it doesn't say that it's a particular instant. It says the top of a ladder at any point in time slides down a vertical wall at a rate of 0.15. So that's the top, how fast it's going down on. And because it's going down, we have to be careful because this distance increases. This one decreases. So we may have to think in terms of the signs, right? So the rate of change when a distance decreases, the rate of change is negative. When a distance increases, the rate of change is positive.
So dy dt is negative.
So I'm thinking that dy over dt is negative.
Can you say that again, please? Wait, now it's negative and now it's positive.
Okay, so I'm moving away from this wall.
Yes.
I'm increasing the distance from the wall. So my rate is positive. I'm approaching the wall. So if
Smaller.
the distance is decreasing, then the rate of change of the distance with respect to time will be negative because the distance is decreasing. Okay?
Can you make it lower?
Okay, so here it is. We inflate a balloon at a rate of 3 cubic inches per
Sorry,
second.
I'm sorry.
We have a balloon
Yes.
and we pump air in the balloon. So obviously dV over dt is a positive rate because the volume increases. Now we take out the air from the balloon.
It's decreasing.
It's negative. dV over dt will be negative blah, blah, blah.
Okay.
Cubic inches per second. So if we pump in air, the rate of change is positive. If we
So-
take
What exactly in this is decreasing?
this distance is decreasing because the ladder is sliding down.
Okay.
So the rate of change of this distance with respect to time must be negative.
Well, would it be on the other one as well?
It's increasing. This one, it's increasing. That's why I graphed it in the first position, and I graphed it when it's 3 meters away from the wall. But the length of the ladder doesn't change.
Well, so how is, I don't understand how one's decreasing and one's not,
Okay?
because they're both sliding away from the wall,
One's
correct?
moving towards the point of origin, one's moving away from the center.
The top of the ladder is moving across along the y-axis. The bottom of the
Okay.
ladder is moving along the x-axis.
Gotcha, okay, I understand.
So this one is getting closer to 0. This one is further away from 0. Better?
Yes.
Okay. So then dy over dt is negative. Also, what should be h? Right. So then I'll know if there is any error, I know I cannot get an h negative because it's the length of the ladder. Okay. Questions? Is this clear so far? Yes? Okay. So we know that the Pythagorean theorem, this is the situation. This is decreasing. This is increasing. And we would like to differentiate first. Let's take a look. 0 equals 2x dx over dt plus 2y dy over dt.
Why is it 0?
When I differentiate a constant,
Oh.
h doesn't change. It's the length of the ladder, right? Okay, so then we have 2x. I move 1 to the, I will divide, first of all, divide both sides by 2, and I get 0 equals x dx over dt plus y dy over dt. And then I will say that x dy over dt will equal negative y dy over dt. Of course. So this if you remember, whenever we say when, it has to wait till the very end. So I do have dy over dt. This is given to us, which is negative 0.15. So from here, what do we get? I have the dx over dt equals negative, oh, it's all positive now. Right, so 0.15y divided by x. Okay, and I am told now, yes, I am told that dx over dt is 0.2 when x is 3. Yes, go ahead.
How did that become 0.15y over x?
Okay, so I have kept dx over dt on one side and I moved this to the other. So You can do either way. It doesn't matter. But I want to solve for dx over dt because this is what I have. You can solve for dy over dt, but why would you? Because we already have that. It's constant.
I understand that.
Okay.
I just don't understand how.
So this becomes negative 0.15 times negative y, which is at the top. And I'm dividing both sides by x.
So what happened to dy over dt?
Just plug it in.
I just replaced this dy over dt by negative 0.14.
Oh, okay. So that, okay.
Is that okay?
Yes, I didn't.
That's
I
okay.
thought that was negative y times dy over dt minus 50.
No. It's multiplied.
Yes.
So now, next step, dx over dt, when x equals 3, I'm just copying from the top so we see it here, it's 0.2. So I'll say dx over dt, when x is 3, is 0.15y divided by x, x being 3, and this equals 0.2. From this equation, I will be able to determine y. And how much did we get? So this is 0.6 divided by 0.15. So y is 4 meters. So then 3, 4, and okay, let's look at optimization. And then we'll come back to other problems. Bless you.
What if I have another rate of change in my hand?
Yes, please. Absolutely. Thank you very much. Two boats leave a port. Very nice. So two boats leave a port at the same time. One travels west and at 20 miles per hour, and the other travels south at 15 miles per hour. Miles per hour. At what rate is the distance between them changing? Changing 30 minutes after they leave the port. So 30 minutes equals 1/2 of an hour. Because everything is in miles per hour, I cannot ever plug in minutes in the problem. Are you with me? Okay. I'm just checking to see. Okay. So. So again, we have to write a relationship between x, y, and z. So if this is x and this is y, then I have z squared equals x squared plus y squared.
What was in the corner? 30 minutes?
Half hour.
Okay. Very good. It'll allow me to delete the previous video because it uploaded. So I have room now. Okay, so then 2z dz over dt equals 2x dx over dt plus 2y dy over dt. They all change at the same time, well, not with the same rate, but at the same time. They're all functions of time. I will divide both sides by 2 and solve for dz over dt. So 2x dx over dt plus 2y. I just said that I was dividing by 2. Didn't I say that? I just said that. Because I'm trying to see how I can tell my best friend's right there in the back of the room to stop talking. So I was thinking, debating with myself. Do I say something? Do I go there and move one of them in front, or just not say anything?
No, we just.
So I was just debating with myself.
It's okay.
Okay, so z is obviously the square root of x squared plus y squared. And now I can plug in the numbers I have. And when t equals 1/2 of an hour. So I do have dx over dt, which is 20. I do have dy over dt, which is 15. I can determine x and y because I plug in 1/2 an hour, or 0.5, right? 20 times 0.5. This is 20 multiplied by 0.5, 1/2 an hour. And this is 15 multiplied by 0.5. And this is 20 multiplied by 0.5 and everything squared. And of course, this is 15 multiplied by 0.5, everything squared. We'll put them in the equation in a minute. But do we understand what is happening? Yes?
Why is it 20 times 45?
When the time is 1/2 an hour and the speed is 20, the distance covered, which is x, must be rate times time, which is 20 times 0.5. Same thing for y. When time is 1/2 an hour and the speed is 15, the distance y covered is 15 times 1/2 an hour.
Yeah.
And the rates are given to us, 20 and 15. In the same way, we determine the x and y in the denominator. So now let's put everything, I'll put everything raw, and then we'll calculate. So 20 multiplied by 0.5 multiplied by 20 plus, yes, 15 times 0.5 times 15. And everything divided by the square root of 20 times 0.5 squared plus 15 times 0.5 squared. Is this okay? And now what I would recommend, I would put everything in the graphing calculator, like this. With parentheses around the top, 20 multiplied by, oops, I said parentheses, and I didn't do it. Parentheses, 20. So that's 400, 20 times 20, right? 400. And multiply by 0.5, I should just write 200, but never mind. Multiply by 0.5 plus 15 squared to 25, multiplied by 0.5. And then divide by, in parentheses, under the square root. I know it may not pop up, but I will put parentheses. So 20.
10 squared plus.
Yes,
7.5
you're right,
squared.
because 20 times 0.5, that's correct. So I'm just going to write 100, and then plus
7.5 squared.
7.5 squared, indeed. Oops. And close the parenthesis. And I get this. What is the measurement unit? Very good, because it's the distance between those two. Very good.
Is that the answer?
Yes.
I
Jerry?
just did the Pythagorean theorem using the rates of change, and you get the same answer.
Yes.
So you just do that.
So you're saying that,
Because we're trying to find z, or the dz over dt, right?
correct.
So 20 miles an hour is dx over dt, 15 is dy over dt, and we're trying to find dz over dt, so dz dt squared equals the other rates squared, and we get the same.
However, you still have to show the related rates
Okay.
situation. Yeah. Very good. Good catch. Okay, so I'm looking at optimization. That's 4.7. And we are on page 332. We looked at the box, we looked at the poster, we looked at the piece of wire, we looked at the distance between a point and a line. We looked at the resistor problem.
What page are we on?
Let's look at page 334. see 59 in red. I don't know. I don't think we've ever looked at that one. I have no idea. 334. Okay. A baseball team plays in a stadium that holds 55,000 spectators. People. With ticket prices at 10, the average attendance has been 27,000. When ticket prices were lowered to 8, the average attendance rose to 33,000. Find the demand function, assuming that it is linear.
So basically, we gotta find out how to fill the stadium.
Yeah. First of all, we have to find a function. This is not the first part that has nothing to do with optimization, right? We're not asked to maximize anything. And part B, how should ticket prices be set to maximize the revenue? So how will I write the revenue?
Attendance times ticket price.
Yes, price times number of people. So revenue is price times number of people. So let's talk about the demand. And then we'll come back to the revenue, because the revenue is what we want to maximize. We want to maximize revenue. Okay. So if the price is 10, then 27,000. If the price drops to 8, then we have 33,000. We are told a very important key. There is an important key of information here. So let's read the problem one more time, and you'll tell me which is the key piece of information. A baseball team plays in a stadium that holds 55,000 spectators. With ticket prices at 10, the average attendance it's 27,000. When ticket prices were lowered to 8, the average attendance rose to 33. Find the demand function, assuming that it is linear.
Okay.
So what am I given? I am given two ordered pairs, 10, 27,000, and 8, 33,000. And I'm asked to find the demand function because it's linear. Okay, so let's find it. Slope. 33,000 minus 27,000 over 8 minus 10. Do you expect the demand function to be, so when the price decreases, okay, so 33,000 minus 27,000 over 8 minus 10. So the top is,
25.
so 33 minus 27, 6,000, divided by negative 2, which is negative 3,000. Okay, people per dollar. In price, of course. So when the price drops by $1, the average attendance by 3,000. Okay, very good. So then now y minus y1 equals the slope times x minus x1. And we pick any point you want, it doesn't matter. So this is negative 3,000. So I have y minus 27,000 equals negative 3,000 times x minus 10. I use the first point. It doesn't matter which point I use. Y equals negative 3,000x plus 30,000 3,000 times 10, and plus 27,000. So y equals negative 3,000 x plus, I think it's 57.
It is.
Okay. So when we increase the price of the ticket by $1, we get the number of people, the demand, right? Number of people. When we decreases by $2, we get the number of people. So now I can come back and talk about my revenue, because the revenue will be the price, which is x, multiplied by negative 3,000 x plus 57,000, which is negative 3,000 x squared plus 57,000 x. So now the question is, second question, find how should ticket prices be set to maximize revenue?
So would we make that equals 5,000?
So r prime of x will be negative 6,000 x plus 57,000, full stop. So we will set the revenue equal to 0. The rate of change, of course. And we will get x equals 57,000 divided by 6,000. So what do we get? I can simplify by 3.
9.5.
How much?
9.5.
So what does this mean? First of all, I haven't shown that this gives a maximum. I have to show why. Please remember, many of you did not. So this is the revenue. It has a negative slope, so it's definitely positive and negative. So it's definitely a maximum. The leading coefficient is negative, so the function looks like this when I study the sign of the derivative, so it's positive, negative, or you plug in 0 and you'll see it's positive, and plug in 100 and you see it's negative. So this is guaranteed to give a maximum. So what will you say? What will you say to the organizers of,
Charge $9.5.
right, to maximize your profit? So when it's 10, you get such and such. When it's 8, you get such and such. If you keep it at 9.5, you're going to get a maximum possible profit. Okay, anything else that you would like to go back to? We'll do more, but I would like to also cover something else, not just anything else that comes to mind.
Estimating with differentials.
Yes, very good. Very good. Estimating with differentials. That was at the end of chapter
3.
3.
Test examples. Can we just do the walkthrough test?
Yes, anything.
Use
Linear
differentials.
approximations and differentials. Yes, at the end of chapter 3. Yes, any.
Use differentials to estimate tan of 3 degrees.
Of how many?
3.
3 degrees. Very good. Okay. The closest angle that I can think of is 0. and that I can use, right? For tangent, I only know 30 degrees, 45 degrees, and 60 degrees, but they are too far away. So the dx has to be as small as possible. So I'm going to say that this is tangent 0 degrees plus 3 degrees. This is my x, and this is my dx. So this is approximately f of x plus f prime of x dx. Always remember, now you can remember this easier because we've been using the dy, the differential of y. So let me just refresh your memory. A function of x plus a little error in x is approximately f of x plus a little error in y. But this has to be replaced by this. So f of x plus a little error in x. This is the error. 3 is the error from away from 0. Equals f of x plus a little error or an error in y. So now I have to identify what the function is, and it's clearly tangent x. I will need the derivative, so f prime of x equals secant squared x. Obviously, x is 0 degrees or radians, and obviously dx is 3 degrees, but I can never use it. Have to multiply it by 1 degree, which is exactly. So then I have tangent of 30 degrees is approximately tangent of 0 plus secant squared of 0 times 3, I shouldn't put degree, there is no need, pi over 180. Actually, I'm going to erase it, I don't need it. So because cosine at 0 is 1 degree is pi over 180. So pi equals 180, 1 degree equals pi over 180. Say it again. Yes. Yes, I can simplify if that's what you want. Perfect. So tangent 0 is 0. Secant squared 0 is 1. So this is plus pi over 60, or 3.14 approximately over 60. So let's do this and check. So tangent if I plug in degrees, I have to have the degree mode. So I want tangent of 3 degrees. And now I want 3.14 divided by 60. Or I don't want that. I want pi, entire pi, divided by 60. Any questions? Are we ready for this test on Monday?